Wait. Okay. Yeah. Well, maybe it might be about time to get started. Moment. What's that? Maybe I have this. Yeah. Basically, most people have moved across to the Jitsi channel. If we've only got this many people, it probably should work okay. Yeah, it might be easier if we do that, if you guys can move across. I'll give you the link if you need it, or it's actually on the TLUG page. Let's see. Oh, that's the wrong one.
Okay.
Wait. Yep.
Everybody.
Yep. First, maybe wait for the other people to get across. Actually, you're on both. No, let's see. Yeah. I suppose the other way is, can I maybe, okay.
Live streaming.
Oh. Yep. Okay. All right. Let's see. Jitsi, we're moving to the Jitsi channel. Okay. Cool, Louis. Is that everyone? Yeah. Okay, yep, yeah, I think so. We all good? Okay, yeah. Okay. There's someone up there.
Hey.
Hello.
Oh, good. My audio is working this time?
Yep, yeah. We've all moved to the Jitsi channel, so.
Oh, okay.
Yeah.
Let me find that.
Okay, yeah. So, just put that. I'm just message, see if we can get everyone else moved across. Cool.
Yeah, I just got the notice on.
Yep.
On Matrix.
Okay. All right. Is anyone following the chat channel?
You mean just right here in Jitsi?
Well, not this one. any of the other ones we're doing. Just for people who are following, well, if anyone's following on the live stream.
Is there like a live stream that's not here?
There's a YouTube of this. Yep.
Okay. Interesting.
Okay. Okay. Maybe we should get started. Like we usually start these things with they're in the real world, with sort of introductions. So maybe I'll do that. My name's Edward Middleton. Most of you probably know me using Gentoo Linux and Rust a lot now. Do you want Raymond, you want to introduce yourself?
Yeah, sure. You can hear me fine?
Yep.
Yeah. So my name is Raymond Wan, and I am in Hong Kong. I've been here for 9 years. Before that, I was in Tokyo and Kyoto. I am a researcher at the university working in now diabetes, and I use Python, Perl, and R. Previous life, I used to use C. That's about it.
Simon, do you want to say something about yourself?
Hi there, I'm Simon, he's Debian. It's probably been about 10 years since I've joined the TLUG meeting.
Yeah.
Good to be back.
Yep. Justin, you want to say something?
Sure. Hi, everybody. My name's Justin. I'm a software developer. I've been doing a lot of Linux drivers and stuff over the years. Projects come up and basically into the internals of the kernel and whatnot. And I've been doing that for a long time and been coming to TLUG now for, I don't know, 5 years, 6 years or so, on and off. And so it's been kind of a cool group. Nice that we can do it online and I guess get to meet some of the people overseas finally. But nice to meet you guys that haven't met. And it's nice that I got a meeting going here.
Michael, you
Yep.
say a few
Michael?
words? Or?
Yeah, my name is Michael. I was a long-term PC Club member and president for a while before it faded. I'm a long-term Linux user. These days doing a lot with single board computers and sensor systems to measure manufacturing process. That's about it.
Christian, are you there? Oh, Christian, sorry.
Yes. Hi, I'm Christian, living since 5 years in Tokyo, working around Linux and looking forward to learn something about Rust. Thanks.
So James, you want to say a few words?
Sure. Hi, I'm Jens. I haven't been to TLUG for many years either. I used to be in Japan. I use Fedora and work on Fedora, and also quite interested in Haskell. And I'm now based in Singapore. Looking forward to the talk. Thanks.
Cool. Jim, you want to say a few words?
Hi, I'm Jim. I've been coming to TLUG for 25 or 26 years. I do a variety of software, mostly trying to help tertiary education move into the 20th century. do everything from OCaml, Python, and Forth. I've been playing a lot with retro computing lately and little single board Z80 computers.
Who's on the top?
Who's that, Stephen? Is that you?
Well, for me, I'm on the bottom,
Yeah.
but
Okay, yeah, sorry.
On the bottom for me,
Yeah,
too.
it's kind of like Hollywood Squares, I guess.
Yeah.
I'm Stephen Lassiter. I guess I've been with the group for a couple years, maybe. Been using Linux since, Slackware 95, I think.
Actually, that might have been the first one I ever used too. Cool.
Yeah. Yeah, Walnut Creek CD. I use Fedora these days. I got my whole family on it. And I just love tooling around with Linux.
Cool. All right. Well, I guess I better actually get started then. So, let's see. Let me share this. Can everyone see that, or?
Looks good here.
All right. I'll maybe start. Who am I? I've been developing software for about 20 years, mostly web development in the last 12 years, a lot of Ruby on Rails, JavaScript, React. I've done some Haskell and some Ember, and back-end sort of stuff in Docker and Chef and all the various other sort of back-endy things. I started using Rust this year. I don't have any specific special knowledge other than having used Rust for about a year. So if I'm wrong on anything, feel free to correct me. These are basically, I'm not going to give a comprehensive coverage of the language because there are bits that I'm still not using, and it's a fairly large topic, as I found just looking at the stuff that I've already looked at. What I'm going to talk about is the history of the Rust language, memory safety, because that's kind of one of the big reasons why you'd use Rust. I'm going to look at the language a bit and some of the things that are interesting in it. I'm going to look at what other people are using it for. It's kind of looking at what other people are using it for kind of gives you some idea about the breadth of what you can do with the language. And finally, I'm going to talk about a couple of projects that I'm doing with Rust. This actually, I sort of poached this a bit from a presentation on the history of Rust. I'll give a link to that later, but in that, the presenter used basically a bunch of periods to kind of talk about the different stages of the development of the Rust language. And from 26 to 2010, basically it was a single person project. I think from 2010 to 12, it was taken on, I think, as a Mozilla project, and a lot more people got involved. From 2012 to 14, a lot of people involved in functional programming and doing Haskell and that sort of thing got involved with it and really made some big improvements in the language. From about 2015-16, it went from being a sort of an experimental thing to most of the changes were made towards making it a solid language and finalizing the language and releasing it as a production language. And from about 2006 till now, people have started using it in production for real applications. Gordon Ha was the original author, and yeah, from 2006 to 2009, it was his personal project. At that time, the things that he was looking at were memory safety, basically not having pointers that pointed to nothing, and all sort of issues you have, or you can have with pointers in C. He had some type state system which is no longer in the language, and I'm not all that clear on the details, but it's another a part of another way of controlling what functionality is available depending on the different states of something. Mutability controls. Yeah. Okay. Yeah. In Rust, there's a it's very strict about whether you have the rights to change something, or whether it's read only, and yeah, sort of comes further in the language. A side effect control that Rust has changed quite a lot, and a lot of these things no longer are strictly enforced in the language. Okay, yeah, you can break the rules, yeah, authorize where and how, yeah. Anyway, in sort of looking at, in developing the language, one of the things that came up was Weyler's law, which is something the guy who's sort of involved in Haskell came up with, which basically talks about in languages, you know, people have very little opinions on semantics usually. Syntactics, more people have opinions on, and usually the further you go down, more people have opinions on them. But conversely, they're less important. Sort of similar to the idea of bike shedding, where you know, everyone has an opinion on the least important things because they're easy to have opinions on. This is sort of an interesting thing in terms of the Rust language, because a lot of the beginning time of the development of Rust language, they were mostly dealing with semantics, and so that a lot of the syntax wasn't considered very much, and also it changed a lot sort of in the process of the development of the language. And in the past, there's been a fair bit of criticism of Rust of being, you know, seeming rudderless, because there was a lot of changes in the language in the process of its development, and it looked to some people like they just didn't know what they were doing. But a lot of the changes were due to thinking about the syntax and the semantics and the syntax, and trying to get that right before making it into a concrete language. Yeah, around 2010 to 12. Yeah, basically, I think Graydon brought in lots more people and sort of acted somewhat like, I guess, the Linus Torvalds or whatever in the kernel. But I gather he was much less outspoken. At that time, initially the compiler was written in OCaml, and from 2010 there was a rewrite of Rust in Rust, which was kind of interesting because at that point in time the language was still fairly early on and was still sort of evolving. They did that on top of LVM, which meant that it actually supported a whole bunch of stuff. But while they were doing that, they also started rewriting Gecko, which is the HTML engine in Mozilla. They started writing that in Rust, which is a fairly ambitious project in itself, but then writing that in a language which is still being evolving is also an interesting proposition.
Can I ask a question?
Yep.
Do you know, was Rust always kind of performance oriented? Like from the beginning, was it intended to be like a kind of a low level performance, or was it garbage collected at one point?
It was actually garbage collected. When at this point, I think to be honest, there's a huge number of changes, and I haven't gone line through line to follow you. Actually, most of this has come off from a presentation which I looked at someone else who I gather had more understanding of the details of the history. It was designed to replace C and C++, because everyone's always been talking forever about how C and C++ have serious issues, and I'm going into later on about, you know, these serious issues that you have in any large project, and yet everyone uses them, and they're used in all the performance critical software, until there's a viable replacement, that would continue to be the case, I think, or that was what the thinking was. And everyone sort of talked about how they need a better language in C because there's issues with C, but this was an attempt to do that, and I think they've actually been fairly successful. I'll getting back onto the history stuff. Yeah, basically in 2011 they managed to compile the Rust compiler with itself. First alpha release in 2002. 2012, Graydon actually stepped down as the maintainer, or like as the sort of benevolent dictator, as I say, which is sort of interesting because from being the driving force behind it to having no single person the driving force behind it, kind of makes a fairly, well, the risk of the project falling apart unless you've got a good community behind it and that sort of thing is kind of fairly big. But apparently he managed to hand it off in a way that, and the community around was strong enough that it's kept on going vibrantly. I was a quote there from Steve. I'm not sure exactly how to pronounce his name. Kubalik, Plabernik. He's actually one of the authors of the main Rust book, Rust programming language books, which is actually online. And he also wrote about a lot of this history, which is, he had the presentation I took some of this, well, most of this information from. This 2012 to 2014, basically they had a lot of people from a functional programming background got involved in the project, and the language changed in a lot of ways where things that were previously part of the language, actually they worked out that they didn't need to be fundamental parts of the language. They could be extracted out into libraries, and that simplified and changed the language a lot. Things like garbage collection. It initially had a garbage collector, like a garbage collection based memory management, and that was actually removed, which it's sort of an interesting thing for a modern language. They also removed this type state, which was considered at the time to be, very important, when it initially came in, it was thought to be very important towards improving the language, and then at this time they removed it because they found it wasn't actually being used. They also adopted, there's an RFP-based process for proposing changes to the language, similar to the one Python has. They actually based it on Python's method, but because there is no benevolent dictator for bringing in changes, they actually have a process where they discuss, and it gets reviewed, and that is for everyone who's involved in the process. So it's not an individual person deciding; it's actually kind of agreed on by everyone. July 2040. I think they finally removed the garbage collection and also brought in a couple of tools. First stable release was 2005. They made some improvements to the compiler speed. Rust doesn't have a formal language specification. It has sort of evolved and is still changing. The Rust Denomicon basically seems to be a documentation of what the language currently is, and that's not really a formal spec. Windows got Tier 1 support, or basically as a language properly supported in October, December. They had one of the big advantages or benefits in Rust is the tooling around Rust that makes it really easy to program a lot of stuff. Part of this, or the biggest part of this, is a thing called cargo, which makes it very easy to manage packages in the same sort of way that you would with something like Ruby or Python, where you can easily pull in packages into your application. Cargo basically lets you do that, and it fills a lot of the roles that you would use for make files, but also package management built into that. And that came in 2005. In 2006 they this is an interesting one in terms of embedded systems. libcore is a subset of the standard library for Rust that actually doesn't require OS features and memory allocation, which has been really interesting because that's made the language possible to be used in a whole lot of different ways that other languages can't so easily do. Things like using it in WebAssembly, where you don't have you don't have system memory allocators. It's also used in things like extended Berkeley packet filters, so you can write Rust programs that'll run in the kernel. But yeah, using this subset of the standard library that doesn't use OS features, you can do that easily. The other one was in July they added support for making Rust programs that can be used as standard libraries for other things, which basically allows you to do things like a lot of the cases where you would write a C library to improve the performance of some aspect of an application. You could now do that easily with Rust, and so replacing sort of performance enhancements and bits. Workspace is also an interesting one. Type operator, I'm going to get into more, talking about error handling. Rust is very good in the way it handles errors. It makes it very easy to properly handle all error cases, and part of that is this operator that they've added. RustUp is basically a tool for installing the tool chain, which came in December 2006. Procedural derived procedural macros are basically a macro system that lets you make enhancements to the compiler. This has been useful for a number of extensions that have allowed basically people to write extensions that do a lot of the heavy lifting of coding complex repetitive tasks, such as wrapping objects. Actually, one of the biggest one they have is there's a simple way that you can automatically generate functions for mapping JavaScript to a structure, and it's using procedural macros. Your Rust build, actually they moved all the build chain to using Cargo so that you could build the compiler with the same tools you use to build your applications. There's associated constants. Allows you to put constants in a whole bunch of interesting places. Incremental copy. One of the big issues that's always been, and still to some extent, is Rust compiling can take some time because it does a lot of things. They added incremental compiling, which allows you to massively reduce the time of compiling when you're actually developing, rather than just compiling a massive thing. Okay, yeah, I'm going to talk about traits later. Yeah, they actually factored out the memory allocator, which is sort of interesting because going back to the earlier stuff where they libcore, where they took out all the operating system specific functions and made a library, a standard library with that. They also created a standard interface for memory allocation, so that what that meant is you could actually write your own memory allocator, so that you could change the way memory was allocated, and that has been extremely useful for a lot of these cases where there isn't an OS there. Things like WebAssembly, well, one of them, or embedded systems, maybe. Yeah, okay. In December, they basically committed to not changing the library. Sorry, not changing the language in backward incompatible ways. So in 2008, basically that they finalized that. There's still obviously changes to the language, and there's still ongoing changes to the language, but they're required to be backward compatible, so you can still compile programs with a newer version of the compiler without having any problems. There's also modular constant functions. Yeah, constant functions, interesting thing they have. At compile time, if you actually wanted to include some data inside your application, constant functions will let you run a function that generates some data, and then it'll embed that actual result data in your application. This, if you wanted, for example, to write a web application that generates some HTML, and you wanted to embed the HTML, and you wanted to maybe run a minimizer, or you wanted to do some changes to it, and then store the actual result in the exe, you could use that for that. But it's also, there's other sort of usages. They also brought out some tools to fix changes, but also to lint and fix to change into a standard formatting for Rust.
Can I make a comment or question or whatever?
Yep.
I think the additions since version 1.0, they guaranteed it would be backwards compatible, like almost completely backwards compatible, right? And I think the 18 edition was not compatible, which is why they kind of made it a separate edition, so you can choose whether you want the new features or the original features, right?
Okay, you could be right.
That was my understanding. Is the 2015 edition is how they released it at 1.0, and that'll be compatible forever. But if you want the new uncompatible features, you can opt into the 18 edition.
Okay. Thanks for the correction.
Okay.
2009. One of the things, a lot more people are starting to use it in production, and up till now, you would pull in libraries that you were using from the public repository. But obviously, if you're doing stuff that you don't want to release publicly, that doesn't work very well. So they added support for alternate crate registries, so that you can still manage all your libraries through this crate system, but you could also use private crate repositories. Big change they released last year was asynchronous wait, which basically is sort of like green threads or coroutines. It's a sort of it's futures basically. So it allows you to run stuff concurrently on without using native threads, which when you're trying to squeeze performance out of systems where there's a lot of waiting, I guess like high loaded web servers and things like that, it's really useful for that sort of thing. Slice pattern matching, that's something that came in this year. I'll get into pattern matching later, but basically it lets you match parts of what are like arrays. So you could match like the first 3 elements of an array or the last element of an array. It's a slice, so it's not actually an array as such. But anyway, that's basically the whole history of it. Yeah, the first bit was just a single project, grade in years 2002. The type system years where they made a lot of refinements to the language and added a lot of functional changes into it, removed stuff from the language and moved a lot of it into libraries. The release years where a lot of the changes they made were just about, well, actually there was a lot of syntax changes at this time because some of the original syntax was kind of difficult or not so intuitive for some people. And yeah, production years where basically people started using it for real things. Memory safety. This is basically a bunch of data that I pulled out from a number of other people's talks on what were the biggest causes of serious errors in different projects. And yeah, apparently memory safety issues are 70% of the serious issues with Google Chrome or whatever. Firefox 72%. I don't really know much about Google Project Zero, but I gather it's some sort of project on working out the causes of 0 days and what the breakup of them. But anyway, they reckon 81% are memory safety related. There's a Microsoft has actually put out some stuff based on their analysis of their historical data on errors, and 70% of their errors are memory related. And it's actually interesting. They've got a graph of this, and it's almost flat. So it hasn't changed. It hasn't got better. It hasn't got worse, which is sort of interesting because a lot of people have been bringing in tools for trying to fix issues with memory safety with C and C++. OS X also, I think this was an estimate anyway of 88%. The Ubuntu and the Android ones I think were based on reported errors. But either way, the majority of issues people, or the majority of serious bugs people are having are with memory errors, or memory safety issues. But going from memory safety issues, Rust, one of the big standout points of Rust is that it actually it was designed to try and resolve some of these issues. And actually, sorry, just a sec. There's a couple of things I wanted to show. Okay. 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 Yeah. Sorry. Just a sec. Yeah. All right. Yeah, this is some metadata. Actually, what's the common weakness enumerated database, but looking at the errors in this, which they've recently they've tried to break these down into more fine-grained errors, so that things like this improper normalization of web input data has actually become a higher thing than memory-related issues before. But yeah, out-of-bounds writes are basically memory-related issues. Out-of-bounds reads are the same thing. Improper restrictions, special. Yes. use after free is also memory related. But yeah, a lot of current errors are all memory related issues. Okay. All right. Yeah. Yeah. Sorry, I'm gonna switch back to. Okay. Yeah.
I saw a null pointer dereference on that list. I'm surprised that leads to on that
I'll just take
weakness list. I saw null pointer dereference on there. I'm surprised that doesn't just crash programs. I'm surprised it actually leads to security issues.
Yeah, sorry, yeah. There we go. Sorry, I'll just null pointer.
These weaknesses, they're security related, right?
Yeah, yeah.
Interesting. Improper check. I wonder if this is like some of that C stuff where, you know, the compiler optimizes out your null checks because it sort of proves that they can't be null because of undefined behavior issues.
Yeah,
Interesting. Well, they got C all over the place there.
Yep. Yeah, that's the interesting one with looking through all these different error types, and it's like the canonical example is C.
Yeah, I bet C's all over the place in here.
Yeah. But I mean, this one's also, I think they're saying it's also, applicable platforms, pretty much everything. Not everything, but yeah. Oh yeah, Java. How you? This is how you do it in Java. But yeah, some of these things have actually been fixed in other languages like Java and C#. Some of them haven't. Let's switch back.
That's so surprising. I'd expect Java to be C# just to be memory safe. You know, like you shouldn't even be able to have those issues.
Yep. Sorry. Yeah. Well, I think Java, you can still have null pointers, can't you, or something? To be honest, I can't comment on Java because I haven't used it for so long. I can't remember, but most languages deal with, most modern languages to deal with memory management have gone to using garbage collection, and that's a big difference, one of the big differences that Rust has. It uses a different method, basically called borrow. It has a thing called the borrow checker, which strictly manages access to memory. And from a description of it before actually using it, it kind of sounds diabolical. It sounds like a lot of extra work. And it sounds sort of intractable, which I think is a lot of the reasons why a lot of people who've made new languages have just gone with garbage collection. Garbage collection's interesting because it kind of removes the whole problem from the application space, but it doesn't come without a cost. There's a cost basically in resources, but it also makes it easy to do things which aren't really optimal, like copying things rather than reusing them, allocating lots of small things in memory, Rust Rust, yeah, basically has gone a different tack with that, and has gone to a sort of more strict model where you manage the memory. But yeah, anyway, it sort of works reasonably well. Rust, one of the other big features of Rust is its generics, which make a lot of the, its type system, which is fairly strict. It makes a lot of those things workable. A lot of people have gone to Rust from languages like Python or Ruby, where, you know, basically you've thrown away the type system and you're not type checking, so it's easy, but it's easy to have things that could have been picked up in a type checking system at compile time occurring at runtime. Yeah. Rust has an interest like error handling, which is more like Haskell with basically, yeah, I'll get into that a bit more, but it's sort of its standard way of error handling is a lot more like the way Haskell handles errors. Yeah, it has a good micro system which can both allow you to write plugins or enhancements to the compiler, but also doing a lot of the sort of straight substitution type of stuff that you would do in a C program. But the micros are hygienic in Rust, so yeah, they're a lot safer to use. Yeah, I'll get into the final bit, sort of talk about tooling. Yeah, each value in Rust has a variable that's called its owner. Basically, you're in Rust, your resources, things like variables, all have a specific owner at a specific point in time. And if you're not the owner, you can't access them. So, for example, if one thread wants to access memory from another thread, it can't because it doesn't own, like the other thread owns that memory that's accessing. Yeah, you can only have one owner at a time, so you can't have two simultaneous things using it. When an owner goes out of scope, the memory associated with it is dropped. So, for example, if you've got a function and you use a bunch of variables in that function, when you leave that function, those variables are going to be freed. Okay, yeah. There's a distinction between values that are stored on the stack and sorry, variable answer. Yeah, if you have, actually, maybe I'll just go to the next video. Yeah, okay, yeah, sorry, yes. Yeah, with assignments, basically, if you assign a variable, actually, I might, it's actually better, some examples of this that might make it easy to, sorry. Yeah, okay. Yeah, I might. Yeah, this is basically a blog post that was done by, yeah, what's his name? Faster than Lime. I don't know actually what his real name is, but here's some examples basically of things like assignment. Yeah, this is basically a declaration of a variable, assigning it a value. Sorry, I'm scrolling on the wrong thing. You can assign a value. Okay. Rust also can guess the type of a value in a lot of cases. So it doesn't require you in all cases to actually put in the case. It's similar in the way Haskell can determine, you know, the type of some cases. So it is not actually necessary to always put in a type. This is an example here where, you know, you're explicitly saying X has a type of I32. Okay. Yeah, okay, there you've got an assignment. Yeah, this is an example of Rust won't let you do a, you know, like a user null pointer. It's basically, in this case, you've defined X as a variable, but you haven't assigned it to anything, so it's pointing at nothing. Yeah, Rust is going to throw an error on that. Yeah, let's see, underscore what we've got. Yeah. Yeah. Yeah, you can override values in Rust, so you can basically assign the same value, like, but the initial value is then lost. And it's actually, sorry, we've got some better examples. Sorry.
Do all variables work like that, or you just always rebind?
The heap. Basically, if you've got small variables like numbers or integers and things like that, they're always assigned on the stack because, you know, they're small, there's no cost. Whereas if you, for example, doing something that's an unknown size like a string or a data structure, it's going to be on the heap. And when you assign something that is on the stack, it'll copy. So it'll just, like, if you know, say this equals this, it'll just copy the value. Whereas if you assign something that's like a string, it actually moves it to the new variable. So if you've got one variable that you say, you know, actually, I suppose maybe an example in code. I'll just gonna let's see, application. Oh, okay. I'm not seeing. Oh, there we go. Okay, yeah. For example, if we say let X equal 1, let Y equal X, that's actually copying X, like, because this is on the stack. Sorry, yeah, I need one of those. Because that's on the stack, that's actually copying X to a new variable Y. So I think at that point when we can still use X, yeah, because these are becoming two different things now. Whereas for a string, because it's actually on the stack, if I went ls1 equals string from whatever, and let s2 equal s1, ln s1, that should not work. See if it's in the terminal. Just a sec. Nope, it did work. Okay, what am I doing here? Let's see. Sorry. Yeah.
Did it? Is that the right?
No. The problem is actually I'm sorry. What I was actually doing is making this function in a library that wasn't actually attached to the program. Here, I think, yeah, it's going to do the. Yeah. This is the main function. I'll just add it here. So Okay. But all right. So yes. No, not. Okay. Yeah. See, it's basically this is on the stack here. So what it actually is doing is it's copying the value of x to y. But the string is actually, it's a pointer to the hash, so the heap. And so if I copy this, what it's actually doing is it's not copying the pointer, which would give you 2 pointers to the same bit on the heap. It's actually moving S1 to S2. So from this point onwards, you can't use S2. It comes up with an error, borrowed of moved value, because it's moved the value from S1 to S2. And the reason it does this is because you don't want to copy what could be, something that's on the heap could be arbitrarily large. You know, it could be an entire video stream or something like that. And so you don't want that automatically copied to something else. So basically, what this is doing in when you're dealing with something on the heap is you're changing the ownership of it. So it's now it's owned basically by 2 rather than 1, which means that past that point you can't use it through S1 because S1's become invalidated. But yeah, let's see. That being said, you could, there are ways to get around this. For example, you can clone it. And what that does is make a copy of it. It's an explicit thing. You're making a copy of what's on the heap. There are also, for example, if this is a structure, that you've generated. For example, we've got a strat. And you've got A equals a string, and B equals, I don't know, to, okay. Okay. Yes, never used. We can implement copy. There's a thing called a trait, which will allow us to do an assignment where it actually copies for a specific structure we generate. So the general case is that anything on the heap will assign ownership when you do an equals, but you can actually make your structures, if for a particular reason you actually want it to be copying when you do an assignment, you can actually override that. Yeah, you can add what's called a copy trait. I'll get into traits next, I think.
If you don't have that copy trait, is it just an error if you try to clone it?
If you don't have it, sorry?
Like, if you don't have a copy trait and then you do like this .clone or something, does it give you an error?
Oh, no, sorry. There is a clone trait, and most things, a lot of things support clone trait.
That's different.
You can copy, but you generally don't want to have it explicit. Like, you don't want to have it automatically copying.
Right.
Basically, there's a lot of things that there might be cases where you want it copied, but you don't want it just sort of automatically copying because it could be a huge data structure. It could be, like, for example, if you've had a buffer or something like that, it could be a huge amount of memory. So you don't want it just automatically copying. You'd want it being assigned first. But then, there are cases where you'd want to explicitly say, well, no, I actually want to copy it, in which case you'd use clone. And then if there are cases maybe where you're always using clone for this and you really do just want to copy it all the time, in which case you'd implement a copy trait. And that way, if you did an assignment, it would actually copy the data.
Interesting. Okay.
Interesting. But the idea about these things is, or the way these things work, kind of encourage you to handle memory sensibly and to, like the defaults are generally the right way to do things. And if you're needing, for the general case, the defaults are the right way to do them. So, I mean, there are going to be exceptions where you want to actually do something slightly different, but generally it just kind of works the right way and the way you'd expect it to.
Yeah, it's nice to have that option. In C++, you can just make some subtle mistake you can't even tell, and it may be copying and allocating memory. It's really kind of hard to know if you've made some tiny mistake that's going to change it from no copy to massive copying and allocating.
Yeah. And I mean, with some of these too, though, I mean, does also rely on the people making libraries to think sensibly about things, because I mean, obviously you could just implement copy trait for ridiculous structures as well, but generally people don't, you know, they're conservative in what they implement, and they implement things that make sense at the time. So, you know, things that you wouldn't expect, well, generally structures and that sort of thing won't have implemented copy trait, just because, you know, they're the sort of things that you'd want to explicitly do. Yeah,
I'm okay. Yeah, that makes sense. I mean, if somebody explicitly makes the decision, that's good. You know, as compared to C++, where by default who knows what you're doing.
Yeah.
At least you got to opt into the thing that you may not want in every case.
Yeah. Well, it tends to mean that it's easiest to do things in the way that makes the most sense, and that's kind of a lot of that is why it actually, even though having a fairly strict system sounds like it'd be terrible, actually works out quite well, because the right way is usually the easiest way. Or, you know, the most efficient way is usually the easiest way. I mean, it's not always the case, and you know, you can't solve every problem. It makes the easy things generally easy, but you know, there are obviously hard things, and that can end up being hard. But yeah, it works quite nicely. So what do you got? Yeah, actually, this another thing, you can't implement the copy trait if there's no drop trait. The drop, like basically, for things being deallocated, you know, we say, you know, when something runs out of like it no longer runs out of a function, or it no longer has an owner, and then it gets deallocated. For things like structures, you actually have to add, what's it say? Can I reproduce by implementing? Sorry, I'm just going to stop this for a sec and get back to the slides. Yeah, you can override a particular case by implementing copy. Okay, so you said there's no drop trait. Okay.
What's that?
Well, basically a drop trait is a method for how to handle when it goes out, like gets removed.
What does that have to do with the copy? You can or can't have that with a copy?
Well, you can't. If you've got a drop trait, you can't add a copy. So in other words, if your structure requires to have some sort of cleanup. I mean, for example, I guess if you open a file or something like that and you want the file pointer to be cleaned up when it goes out of scope, that would be a case where you couldn't implement copy.
That kind of makes sense, though. So I guess copy is more just for memory that you can just free.
Well, copy just basically makes it easier. I mean, it means you don't have to write clone. So you don't have to explicitly, and it'll handle it like it's, you know, a smaller variable.
Yeah, that makes sense for like memory, but not for like file descriptors, because you can't really copy those reasonably anyway.
Yeah.
Okay.
Yeah. Okay. Yeah. Now we looked at the moment we looked at just assignments, but then there's also functions with you know, whether you functions work similar in terms of whether you move or copy the arguments. If it's a structure, you actually move it, but and that actually has some sort of implications which you need to think through. I might switch across. In the same way for things like integers, if you send an integer to a function, it just copies it. It doesn't it doesn't move the ownership to the function. When you return a value, it actually moves the value out of the function. But one of the consequences of this is you can't do something like inside a function. Actually, inside a function, you can't allocate a variable and then return a reference to it from outside the function, because the variable will go out of scope. The variable, because it's in the function, it's scoped into that function. So at the end of the function, it'll disappear. So you can't return a reference to it. But I'll pop a source code example and application. Where are we? That one. Yeah. What this basically means is let's sort of make a function and we're going to pass it a string 1 and a num u32, and we'll have nothing returned to start with. Okay, let's get rid of that for the moment. Okay, so we've got a function there, and let's kill this one. And so we'll let s1 equal string from something or other. There. And let I'll just call s and n, so it's not okay. And we're going to call my with s and n. Okay. At the moment, the function is not going to actually do anything, but it demonstrates how passing. I
don't think I can see what you're doing.
Sorry?
I don't think I can see what you're doing. Is it just me, or are you in a different window?
No, it looks like he's not sharing.
Okay. I'll stop sharing and reshare again. It's showing for sharing for me, so I figured it was. But can you see that now?
I mean, you're sharing, but not the window you were typing in. It's the same window as there from before.
I should be sharing a source window.
Right, but I'm not seeing you type any structs or anything like that.
Okay, no, I lose the structs. You don't need that. Actually, sorry, I'll do a string anyway. We'll just use a string because it's a simpler example. A string's similar to a struct. Are you seeing that now?
It's
I'm not.
on the same screen.
I'm just looking at Jitsu too. Oh, sorry, I'm looking at the YouTube and it's not showing anything.
I think it must just be stuck. This must be the last image that came through.
Okay.
Yeah, I think I had this problem too when I used Jitsi this week. That some people weren't seeing what I was sharing, and yeah.
Yeah, it's not showing up on YouTube either. Maybe if I do a full screen share, that's not going to work so well. Is anyone seeing that?
Still the same thing as before.
This is
Okay,
main.
Sorry?
I can just see the main RS file.
Yeah, it kind of flickered like you changed something, but then it just came back with that same old image.
Okay, maybe if I leave and return. All right, I'm just going to do that. Just be a sec. Okay. Can everyone hear me?
I can.
Okay.
Oh, that looks better.
Okay. All right. Yeah, basically, we're passing something that's on the heap, and we're passing something that's on the stack. And yeah, we're passing it to this function. Now we're going to try and just demonstrate what's actually happening here by okay, let's see. Now we're trying to use s, which is our string, after we've passed it the function. What's actually happening when this function call happens is it's actually passing s to the function, so it's now owned by the function. And so past this point, we can't, that s no longer exists. If we look at println, let's see, with our number is actually just being copied. So because number's copied, you can still use that outside because number is on the stack. Of course, that's not, sorry. We could, of course, because we've moved this string into this function, we could actually move it back out again. So if we did, for example, which I think we can do this. Okay, no, I think it's just doing error because S1. Yep, that's right. Okay, so here what we're basically doing, we're moving S1 into this function here. And then, in Rust, you don't actually need to type return. If the last argument is a value, then you can actually, you don't need to write return. You can just put the value. So basically what this is doing is it's saying, oh, we've got a function that returns a string, and we're moving it back out as a return value of this string. So if we could actually do let g, well, I think we could do this. Yeah.
Okay, so the error went away when you did that.
Sorry?
The error went away on your S there.
Yeah, I'm thinking though, maybe might be getting something wrong here, but okay, yeah, no, because this isn't, what I'm actually doing is, what I can't do is this, because that's trying to reassign S. But this is actually creating a new S and assigning the output value to that S. Basically, at the moment, these are constants, or not constants, but they're not immutable, both these values. If we wanted to make them mutable, so for example, if we wanted to be able to say this, we could say S is mutable, and that means, that would allow us to change the value of S, and then, it works as well. But yeah, what we're doing in this case is, in my function, we're moving S into the function, and then we're moving it back out as a return value. And so at any point in time, it's only in one place. It only has one owner. You can...
So, I guess the move is just like C++. Nothing's actually being copied, right? It's just a pointer going in and pointer going out.
No, it's actually, sorry, when it's saying it's moving, it's assigning ownership. Basically, it's saying it's now owned by this function. And because only one thing can own it at the same time, then, if you, until you move it back out again, nothing can access it from outside that thing. This obviously, does have potential issues, because sometimes you might want to actually read-only user value, because it also means things like, let's see. I think that's no. Why is that going to work? Yeah, actually, no. I think I need a struct for this to not work. But yeah, let's see. Yeah, in this case, because it's actually moving it, and then we're moving it back out again. The other thing you can actually do is you can say we don't actually want to return it. We want to pass it as a value that can be modified. And sorry, you can pass it. Well, sorry, you want to pass it by reference. And there's two ways you can pass by reference. We can pass it as, let's see, mutable. Okay, yeah, so we need, that's a reference, so we need to do that. Yeah. What have we got here? Match type string. Oh no, I need to save it. It's okay, yeah. This is nope. Okay, yeah, because this is a string, and that's a string reference. Okay, yeah. Basically, yeah, you can pass a read-only reference to a string, and this is what I'm basically doing here. And you can have, actually, I'll just go just a second. I'm just going to move to the next slide. Yeah, okay, yeah, I'll talk about borrowing now, because the other, let's see, just a sec. Yeah, before we moved a piece of, moved the ownership into the function and moved it back out again. The other thing you can actually do is you can borrow, non-mutably borrow something. This can be useful because in a lot of cases you want to read the value, but you don't actually need to change it. And in those cases, it'll allow you to read, immutably access it by in multiple places by borrowing it multiple times. But none of them, because none of these will have be able to change the value, that doesn't cause issues with memory safety. You can also mutably borrow a reference, but if you mutably borrow a reference, nothing else can. You can't. Only one thing can mutably borrow an item at the same time, which basically avoids, for example, you borrowing a value mutably and then changing it while other things are immutably reading it, which would potentially cause issues. Yeah. Okay. Yeah. Some dangling references. Yeah. Yeah. One of the things I was talking about before was you can't return a value to that's generated inside a function, because that would or you can't have let's see. For example, if we didn't pass this here, instead in our little function here, we just said let s1 equal string from, and then we're going to return s1 as a reference. This won't work because the string is owned by the function, and so that the data is going to go out of scope. So it won't at compile time, it's going to throw an error. And that's what this is actually, the red line here is saying, basically, that you can't do this because, yeah. Okay, sorry, no, that's a different error. There we go, just fix that one. Yeah. This function types, yeah, it's not a static value, so it's going to go out of scope. Yeah. So the lifetime of this.
Oh, it's telling you to make it static, and then you could do it, I guess, right?
Yeah. There are also lifetimes in Rust, which basically allows you to say, okay, this thing will exist. I mean, the situations you run into here where it's not clear whether the value will definitely exist, but you need to be able to tell the compiler that it will definitely exist, because the compiler can't guess that it's going to exist and always be valid. And so, there's a thing called lifetimes, which you can explicitly write lifetimes which tell it that it's going to exist at the same time for the time. In this case, I think it's saying, what if it's static? Let's see. Consider using static lifetime, and then I can't remember. Yeah, actually, I'm not sure whether that. No, okay. Static. Yeah, actually, I can't remember how to pass a value out of a static string. But anyway, yeah. Actually, just a sec. That's the lifetime, I think. So, yeah. Take keyword static. No, all right. Anyway, basically, you there is a way to get around this so that you could actually pass back a value that is assigned if you can indicate that it's going to have a lifetime that goes past the scope of this function. But generally speaking, you can't. It won't let you have a dangling reference to something that's been deallocated in a function. Okay. It's also references must always be valid, so it won't let you generate a reference that can become invalid, or any given time. And what I was saying before about you can only have one. You can have a mutable reference, or you can have multiple immutable references, but you can't have multiple mutable references, because if you could have more than one thing changing the same thing, then you've got potentials for race conditions and other issues. Okay, all right, let's move. Just gonna move back. Let's get next slides. Escape. Sorry, just another sort of thing which I think we got into, or sort of was shown earlier on, was a thing called slices. Slices are references to things like array structures. What they give you is a sub-range of an array, for example. But unlike, for example, a pointer, these are guaranteed to exist because they borrow from the array that they're taken from. So you can't free the array that they're accessing without relinquishing the slice on the array. So basically these are really useful if you want to pass a reference to a larger structure or a sub part of a larger structure in a read-only way. Okay, generics. Basically generics in Rust are one of its really big strong points, and it allows you to do a lot of things that seem like a dynamic language, similar in ease to the way you do them in a dynamic language, because you don't have to explicitly write every single the type system can work out what types things are, so that as long as you implement the right traits, you don't have to be explicitly writing type definitions or actually, I'm going to cut that thought. The way generics are implemented in Rust, generally, there's two ways. You've got monomorphism, where it basically creates a custom function for each instance, which is fast but less memory efficient. It's the default way that it's done, and it actually works very well. The other approach which you can do is using a virtual method table, which I think is more like what C++ uses, where it's dynamically worked out at, or where the functions are kind of dynamically worked out at runtime, which in some cases can be more memory efficient, but in terms of performance, it doesn't work as well. Basically, generics are implemented through what are called traits in Rust. Traits just give you a definition of a bunch of functions that a particular type is going to implement. An example of a trait might be, actually, let's see, find a function. Yeah, maybe I'll go and get some examples of traits that might. Stop sharing. And well, let's write a basic trait. Okay, all right, so trait X, Y, Z. XYZ trait, and we'll have a function do something. All right. Now, for example, we might want to have, say, our function accepts anything that can do something. Our function here, we've got takes one argument, and we'll call it the do something trait. And so we'll do let me save it. Nope. What have I got wrong here? Maybe public. No, I found the. Huh? I think I'm getting this wrong. No, A is not. Okay. No, I'm getting just a sec.
Why do you have the type both in the angle brackets and then as the type of the variable A?
The angle brackets basically says the types that are used in the function, and then they can be used in different places in that function. There's also
C++ template works. Is it like kind of the same type of thing as a C++ template?
I don't know C++ templates. I haven't used them, so I'm not exactly sure. It's basically saying it. I think it's used in this function, so it could be used in an argument or return value or something. I'm just
Inputs
seeing what
are
am I,
a little bit like that. Syntax is kind of similar.
yeah. But yeah, what am I getting wrong here? Sorry, I need to actually have some examples, pre-made examples. Let's see. I have. Okay. Let's just a sec. Yeah. Okay. What are we gonna do? Yeah, I think that's what I need. And something myself. Let's see. We're just going to make a structure and add that trait to the struct. Says, yeah, we don't actually need to do anything. Now, we'll write an implementation of do something for my do thing. Yeah, so what I'm doing basically here is I've got a structure which is going to implement this trait. I'm I've defined in the trait what the trait is, and it's basically one function that's doing something. I've got a struct, and I'm doing implementation of this trait for this particular struct. So I've got to add this function doing or do something. And we're going to, self is a reference to the structure that, because it's referring to itself. So print ln something. Okay. So now my function here, we're going to call it with let's see. S my doing thing. What have I got here? Actually, no, so it's just a struct. So you actually implement a new method to do that. Instead, we're just going to implement S and okay. Let's see. So doing something new, method, and doing something.
I think you need to name it. You're missing the name inside the angle brackets.
The name inside the angle brackets.
You need to say like my type : do something.
Yeah, but then that's.
And then you use my type. as the type.
Yeah, it won't. That'll give you then. I mean, that's basically defining. In that case, I don't actually need need this at all. I could just type my doing thing. Because it's not. That's the non-polymorphic version.
Right. Then you can only pass a my doing thing. But if you want to pass, do something, you need to just say X colon do something and then A colon X. Like you have to name that part in the angle brackets.
Yeah, right. Yeah. Yes, of course. Yeah. Yeah. Sorry. Yeah. Brain fart and AB. Yep. There you go. Yep.
Okay.
And then let's just see. Run it. And, let's see terminal. Yep. Warning something. So yeah. We passed the polymorphic. We used the generic function to do something for.
So this is not. Is this using like the virtual dispatch or the?
This isn't using virtual dispatch. This is actually it actually compiles this version of it, which is faster. There's another way. There's a dynamic. Let's see. I'll just remember the. Okay, no, I've got to actually find. Forgotten the syntax. Yeah, you can also do a dynamic dispatch. I think it's not dynamic. It's something I got to. Which will allow you to change this on the run. So you could change. You could, for example, have a runtime flag where you decide what structure was being passed, and it would use dynamic dispatch to work out how to call the function.
So it's kind of similar. The code would be similar. You just tag it somewhere with the dynamic thing.
Yeah. Sorry.
You don't need to do it.
Yeah. Anyway, if you Google the keyword is dy. Or I think it's dync. And if you do that, then it'll use the dynamic dispatch, which means that you could change these things, change what's being passed dynamically, and it'll use a vtable to kind of work out which function it needs to call.
That's cool. In C++, the syntax is like wildly different for doing this with a template versus doing dynamic dispatch. It's kind of like radically different way of writing it.
Yeah. But yeah, I mean, the syntax is fairly easy, and it's amazing. Like the more you get into Rust, the more of these things you see are just traits, because you can actually even do traits that don't have any methods, and they use one. There's a trait called sized, which is used to indicate things that the size isn't known at compile time. So, for example, an int, what size it's going to be, or a certain type of int, what size it's going to be at compile time. But a string that is allocated, you don't know the size, so it doesn't have the size trait. And that can be used in a whole bunch of different ways. There's also traits to indicate whether something can be passed between threads. I think it's send. But yeah, it's also used in a lot of generic things, like for things that can be iterated over. There's an iterator trait. But yeah. Anyway, go back to slides just a sec. Stop sharing that one and share next slide, I think. Yeah. Sorry. So, yeah. The other thing is too, you can use these traits in structures, in enums and functions, and you can use traits in traits. So you can say, you want something, you want to make a generic structure that can take two types of things of a certain type and return them. And that's actually going to go into, I think, errors. Yeah, error handling. Basically, Rust breaks errors into two types of errors. You have, nothing can be done, throw everything away, crash kind of errors. And, there's a panic keyword for that, which basically is for anything where there isn't a sensible way to handle it, or you don't need any, like the most reasonable thing to do is just stop. Then it also has option and results. And I think they're a bit similar to the way people do a lot of stuff in Haskell, but basically, that's for the cases where there is an expected error and it should be handled. Or option can be a case where, for example, like reading from a source, there might be some data or there might not be data, and so, you have two possibilities. Sorry, just go back. I just want to talk about error handling a bit. Just a second.
Yeah, I always like that about Haskell, after doing C for so long, just trying to encode your errors as like, null pointers or certain integer values or whatever. It was nice to be able to just explicitly say, this is an error or not an error in the data. Yeah.
Actually, just before we get onto errors, another thing that you should look at is enums, which is gonna actually just display the document page, because it's actually kind of pretty. It gives a pretty good example of some of the sort of things you can do with enums. Basically, you can. Enums aren't just. Sorry?
You're stuck on that same Code Explorer window, the IDE window.
Sorry?
The video stuck on the IDE window again. Like, I think you switched the slides for a second, but I was just seeing the code window the whole time.
Oh, all right. Let's see. Are you seeing that now?
Yeah, still the same thing as before, the editor window.
Okay, I'm just going to re-enter.
All right.
Okay. Can you hear?
Yeah, okay, there we go. It updated now.
Okay, yeah. All right. Basically, enums are sort of similar to C enums, but you can do a lot more than just, integer value sort of stuff. So, you can have structures in them. You can have, all sorts of different things. You can also have empty enums. But what this allows you to do is, I'm just going to Rust option. Let's see. Yep. Yeah. With Rust options, basically, Rust options is, I think, let's see, grab the source code. I think it's probably, nope, wrong one. This is the Rust documentation. It's actually pretty good. Fairly easy to use. Basically, if you're returning something that might or might not have data, you think there's an option enum, which has two types. You can have a sum, which is an option that actually returns a value, or none, which returns nothing. And P, in this case, this is actually a generic type, so that you can actually, this can be used for anything. You can decide what P will be, what type P will be. So you can just use this standard option anywhere for any function.
Haskell,
Sorry?
that's interesting. That looks just like Haskell.
Yeah. Well, that is basically, I think, where it came from. The other one too is, let's see, you also got Rust. What do we call it? Result, which is your other option type. Actually, here, I don't know why the other one didn't show the type at the top, but yeah, see, it's basically an enum, and it has two generic types, so you can define what you want the result to be and what type the error should be. And then you can directly define an error if you wanted to, or let's see, we got some examples, maybe not.
Yeah, that's nice. That's a million times better than C.
Yeah, but yeah, it's kind of really useful. It's also this matching deconstruction. Deconstruction is really useful because you can have an enum that's full of a whole bunch of different stuff, and then deconstruct it, pull out what you're interested in. But yeah, anyway, that's the enum. I say that's the results processing. So yeah, you got two generic types. You got results or things. And the other thing too is these aren't built into the language. These are part of the standard library. So yeah, a lot of, I think in the when the language is being sort of finalized. Oh, sorry, I think it's earlier than that. But when a lot of the Haskell programs and other people were coming into being involved with Rust, a lot of these things that were language constructs got moved into just libraries because they could be done in the type system. Oh yeah, like this, the language is actually good enough to do, to implement these things. Yeah. Okay.
That's really cool that they're able to do that.
Yeah. What's one of the really nice things about Rust is just the way, this sort of idea of zero cost abstractions, where basically if you use stuff, there's maybe a cost in using them, but for stuff that you're not using, you're not actually, there's no overhead. And a lot of the way it does this is there's so many things are in libraries. And so you can just opt out of using libraries if you don't want certain things. Like, being able to opt out of using the standard library so that you can write things that, for example, don't have an operating system. So that they can't use functions in the standard library because they can't actually, they don't have an operating system to connect to. Yeah, okay, all right, let's move on to results. Yeah, just going to stop sharing that one. Yeah, tell me if this doesn't update. Actually, just a sec. Why is it? Okay. Okay, yeah. One of the other kind of nice features of Rust is its macros, which in a lot of ways is similar to sort of, well, I suppose, yeah, I think they were designed as a sort of a replacement for C macros, but with, a lot of the issues solved with them. Things like they're hygienic so that you don't have issues with the macros interfering with each other. They're pretty easy to use. They actually they match on the on passed tokens, not on strings. So you can. Some people have used them for writing little macro DSLs inside things. They're also used fairly ubiquitously throughout, the throughout a lot of the basic stuff in the language, in the standard library. Might just actually pop over and look at some of the stuff in the standard library that is implemented through macros. And just be a second. Okay. All right, I think. Sorry, that's not what I was looking for. Yeah. Let's see. Yeah, I've been using in a lot of places this print line command, which is just a macro. This is basically how you define macros. I've forgotten what TT stands for, but yeah, basically. Macros macros are pretty much similar to C sort of macros in a lot of ways. You can, except that you passed a token stream or whatever, so that you've got a match on the tokens, and then you can do various things with that. It's print is one of the sort of common ones. There's a bunch of other sort of things. It's got a macros somewhere here where you can, let's see. Yeah, this is a macro that will let you include binary data from a file inside inside an application, so that you get access like a variable.
Like if we were to look at the code for that macro, there's like something that's actually opening a file, a random file, and reading it and making an array or something.
Yeah. Basically, that's what it's doing. And actually, one of the ones you can actually. I'm just going to show some code, because there's a cute little command actually that will let you evaluate macros and show what the output code would look like. Is this changing for? Oh, okay. Is it changing for everyone?
I can see it.
Yep. Okay. This one. No, we've only really got one macro here. We've got print ln, but let's see. New terminal. So there's a cargo expand. Now what this does is basically evaluate all macros. So this is what those macros, like the generated code from the macro is.
Oh, interesting.
But yeah. But yeah, there are some fairly extremely complicated macros that do lots of things, like generate a whole bunch of functions that they add, or structures, or people built ones around things to allow you to have a structure that when the structure is passed, it actually generates a whole bunch of different functions or things based on the structure, because it's sort of passing the tokens in. They've also got ones. I mean, you basically you could, in theory, write a DSL or something, in a macro, to do sort of custom things. I think there's one for JSON which will generate an internal like a specific type of representation of JSON data. But you just type in the JSON and it'll pass the JSON into that. yeah, so, I mean, there's a lot of things you can do with macros. Mostly I've only looked at the sort of basic stuff with these, where you've got a repeating pattern where you might have to do something 50 times, and pulling it out into a macro massively simplifies the code. But yeah, anyway, let's let's see. Let's get back to the slides. Yeah. Okay, yeah, sorry, yeah. Yeah, one of the really nice things about Rust is the tooling. This is basically the most common stuff you're likely to use. Crate.io is this site that has a whole list of all the libraries everyone's generated. It's sort of similar to what you'd have in Python or Ruby, or various other languages, and it's really easy to pull down the libraries from there. There's a command basically for setting up all the default sort of libraries, all the default files for an application. This is if you want to set up the default libraries for the default files for a lib. Building is just cargo build, that'll just build the executable. You can just do cargo run, where it'll actually build and run any changes. Cargo test, there's built-in, or well, in libraries, the support for running tests automatically, and that's what cargo test does, just like a sort of unit testing framework. Might look at actually.
I heard that there was something you could do, like if you wrote sample code in comments, it would also like compile those and test them or something, doesn't it?
Okay, that was document tests. Yeah, you can write sample code in your documentation, and actually I think I'll go and have a look at the Rust book. I think there's lots of different books that people have written, and let's see. Types. No, that's right. Yeah. Okay. Sorry, just a sec. I'll just find. There's a the sort of Rust reference book actually is has a whole bunch of embedded code in it, and it'll like let you run the programs in it. It's wrong book. Books. Rust programming, I guess, the one I think. Okay, yeah, that's. Okay, just a second. Let's share the page. Yeah, this is the Rust Programming Language book, and they've basically got here's an example in the code, and you can click run, and it'll execute the code and give you the results. You can do similar stuff. You can set up your documentation so it'll do the same thing, I think. To be honest, I've never actually used it, but yeah, you can run tests so that it'll actually try and execute the example code in your documentation, so that it guarantees that your documentation is actually accurate to how the interface currently is. That's kind of useful, I guess, to keep stuff current. But I might just give let's see. Looking at I'll just give an example using the tools basically to set up an application. All right, let's just do a second. I think this is, yep, that's the one. So for example, I want to go generating a new application, new my test bin. All right, so my test, and that's going to generate all the default files. Actually, yeah, even a Git repo. But yeah, the main file, this is your package managing file, and that what that has is a list of the dependencies you have. I'm just going to change Windows and open this up in another. Actually, let's code up, and I'll just change into that window. Application. Oh, not that one. Yeah. Yeah. Okay. So this is just a new app. Let's see. For example, if we wanted to do a dependency as one, for example, we wanted to add this a library for regular expressions. Now, one of the things I kind of like about the integration here is that you can actually, if you don't know what version the most recent version is, you can just save it with the brackets and it'll give you that. But then if we wanted to build our app, then cargo build will pull down all the dependencies for regular expression and then compile it. So basically all you have to do to add a new dependency library is list it in your file, and then cargo will handle all the downloading and installation. There's a lot of different things you can do here. You can put dependencies on tests and that sort of thing, so it's only pulling down stuff relevant to the tests, or in this case we can also do the run, which is just cargo run or run that thing. It's tests as well, but I think it's just going to say there's no test yet. Zero tests and zero test pass. But yeah, this sort of integration, something if you're using Python or Rust, or I think Perl even, you're used to, and it just works really easily. With Rust, it's exactly the same. It's just a matter of adding the dependencies, and it automatically gets pulled in. Yeah, actually, that's another one. You can check all versions, and yeah, the integration. This is using a fork of Visual Studio that takes out most of the Microsoft telemetry stuff, but the integration with that's actually really good. Yeah, it'll show errors and that sort of thing, and
is there
one of the really nice
plugin you need for that, or is it just work out of the box? Is there a plugin you need, or does it just work out of the box?
Yeah, there is a plugin that works pretty well. Actually, yeah, I think when I put in, I just did a Google for. That's the.
Oh, so it's just the standard plugin. The plugin.
Well, I mean, if you just do Google Visual Studio Code and then Rust, it'll give you all the options. They're coming out with a newer one, which is supposed to give even better help on, when there's code mistakes, it gives you even better help. But I mean, the code, it's worth looking at error messages in Rust because they're actually helpful. Most of the time, like especially when you get started, just because the borrow check is different from how other languages handle things, and so it takes a little bit to get used to. The error messages are really helpful for that sort of thing because they're fairly easy to understand what's going wrong, and they're also, I mean, the people who are actually doing the error messages on them, they had a talk at the last Ruby conference, and the guy who's doing the error messages for it is very keen to improve them. So if you find stuff that doesn't make any sense and you can't complain to him about it, he'll probably fix it or make it better. But I mean, the error messages just are really good as is. It's as long as you they explain enough information for you to resolve most issues.
Yeah, that'll be a
They-
nice
I mean,
change from like C++ and templates, or just
Yeah.
pages, error messages that don't make any sense at all.
Yeah. Well, I mean, I think they're basically they would like you to be able to work it all out from that. I think it's probably just because it's a complicated enough language, you can't, there is a limit to what you can expect an error message to tell you, because it can't possibly know exactly what your reason for doing something is.
Yeah, I understand it's difficult to do, but the language shouldn't be designed that way. It should have generics or something that give you a cleaner error message.
Yeah. No. I think what I was trying to say is that Rust, I think, goes pretty close to as far as you can in doing good error messages. I mean, that obviously they could be better in places, and it's always the case. But usually the issues that, when I was starting, the issues I had was not so much with the error messages, it was more with the concepts and things being different. And it's like the error message told me exactly what was wrong. It's just that I wasn't understanding that part of how the language worked, or wasn't understand. I didn't have clear idea about the borrow checker or those sort of things. So like you read the answer and it's like it's obvious. Well, you have to actually do a bit of reading before you kind of start getting into Rust and understand some of the key concepts. It's not like you'd learn by going directly in and trying to write stuff. Just because the borrow checker and that sort of thing are things that aren't in other languages.
Yeah, I mean, I guess you can't expect compiler error messages to really be a tutorial in a sense. At some point, there'd be too verbose for experienced users.
Yeah, but then the way I learned was basically there's a book, the Rust programming language, which is actually, it's even online. You can get it free. It's just a web page with it. But you can also there's the book for it, and there's another actually one from O'Reilly's that's quite good called Programming Rust. But yeah, basically read the book, and then the error messages tell you enough that you can understand what's going wrong, and they're good for learning the language, as opposed to they're not going to teach you the core concepts, but once you understand the core concepts, they can teach you to program in the language, because they give you good enough information that you can understand what went wrong and understand then how you would fix it.
That's cool.
Yeah, but it's just interesting having these sorts of things in a language that is very much like C, in terms of where it's applicable. Because you look at a lot of languages, like things like Java or even Go now. It's interesting, but I was writing server stuff with Go, and I hit the wall on sort of stuff where you had to. I was trying to interoperate with. I was trying to write an API for Google AdWords, and Google makes Go, and Google AdWords API was a real pain in the ass to work through with Go, just because it made some assumptions, and it had a sort of simple model which works easily for certain things, but didn't work very well for trying to implement a SOAP API. Whereas
what I've heard about it is it works good for its narrow kind of use cases.
Yeah.
If you go outside that mold, then you're in trouble.
But Rust really feels more like the sort of language that you could build anything off, or you could, if you're going to implement a specific domain language, starting with Rust, writing it in Rust would make sense. And it seems like there's so many different things that people are actually using it for, because it is flexible enough. A lot of things maybe you could actually write as libraries for Rust. For a specific domain, if you're working on it, you could write that domain as libraries as a Rust, and then implement them quite well. Especially things like the macros just make it so nice for writing specific types of applications or specific sorts of code that you might like domain specific kind of languages and stuff, but or building that sort of thing on top of it. But But yeah, I think when they started out, it was the idea was that it was sort of, you know, a Rust or a C++ replacement that solved the memory issues and those sorts of things. And I think they did a fairly good job of it. And looking at the way it's developing in terms of an ecosystem, I think it's, yeah, heading towards being a really, really powerful language. Actually, yeah, I might just, there's a couple more things I was going to say, and then, I mean, if anyone's got questions, but let's see. Just, okay. But yeah, I mean, the final kind of thing was what are people actually using it for at the moment? There's a lot of people working at web applications because, yeah, they've actually had stuff that's successful and realizing that it's pretty hard scaling a lot of the current web frameworks that are popular. I personally have noticed things like going from Rails stuff where you might, you know, run a, you know, need a gig of memory or whatever, running an instance to run something fairly reasonably sized, but stably run it. You know, you're talking like 100 meg if you're running it in Rust, just because it's so much more memory efficient, and you're also getting a really big boost in performance. WebAssembly is really interesting too, because it gives you the sort of all the advantage of the language, but also being able to compile it to something that'll run fast on a browser. I've played around with a bit of WebAssembly, and at the moment there's still sort of limitations in WebAssembly in that a lot of the stuff that you use, you actually have to run through the JavaScript to get access to certain things. But the performance is really good in WebAssembly. The other one is Berkeley packet filters. There's an interesting article the last couple of days. I'm just going to grab it. Actually, yeah, this is, let's see, sorry, I'm just going to share this one. But yeah, this guy's basically been working on, yeah, writing BPF code in Rust. And, you know, what it does is it gives you access to a lot of the internal, a lot of the APIs in the kernel. And, you know, you can use it for lots of sort of debugging, deep level debugging stuff. But one of the ones he actually did an article on looking at Zoom and using this to gain access through the kernel to the data, pre-encrypted data from Zoom, and, you know, using that he could actually look at some of the things that they were doing in talking about they were using OpenSSL, and he could actually pull the data out before it became encrypted, before sending it. And, you know, because he was instrumenting that at the OS level, you know, you could effectively do that on any application. But it was just sort of an interesting use of these sort of things. You know, sort of deep diagnostic stuff, or looking, you know, what things are doing. Let's see, yeah, there's a lot of people in the gaming, like who are writing games in it too, just because of the performance is so good. This one, a guy who's writing sorry, just a sec. Yeah. It's a blog post by a guy who basically started writing an operating system in it. And that's sort of interesting because a lot of the like this came into before what I was talking about with having a standard library that doesn't actually require an operating system. You can't use a standard library that requires an operating system when you're writing an operating system, because you don't have, all that sort of side of it. But because they actually have a subset standard library that, doesn't need any of that, you can actually write easily enough an operating system in Rust. But yeah, sort of interesting that someone would try it, and with this they've actually got code and things. So if you want to have a kind of look, you can compile it up and run it yourself. What was the other one? Yeah, a lot of people are starting to use it in embedded as well, just because it's so efficient in memory usage, and it's also it has all the advantages of memory safety and the efficiencies of memory usage and that sort of thing. So it's people who are using it for both embedded systems, but also things like microcontrollers. The final one I was going to talk about. Just the projects I've been sort of using it for. Let's see. Yeah. Okay. Yeah. I was using WebRTC to try and start implementing a video conferencing software using WebRTC. I also looking at there's a command if you've used AWS as a command line tool, called AWS, that lets you basically use all the APIs that they have as a command line tool, and works really well. The only problem is it's like a lot of Python applications, there's a huge number of libraries and dependencies that you need to install it. And what I was trying to do is see how difficult it would be porting the Python to Rust. And it turned out actually that was fairly easy, which is it was a bit surprising because the languages are very different. But I got to the level of some basic interactions with S3, like listing files and that sort of thing, and that's worked quite well. I'm still in the process of sorting out uploading and downloading and copying between repos. But other thing, in the final project I've been working on, which is probably the biggest one, was I have a bunch of servers at home that are old enough that they use a HP Internet Lights Out 2 console to remotely view them. And that basically gives you a remote console that you can interact with the BIOS and stuff like that while it's booting, or reboot the system or stop the system. The problem is that it's so old that it's using SSL that no browser supports. And so basically I've been re-implementing the protocol that they're using to transmit video, or interact with the server, which hopefully by the time I finish, it'll mean I can just run a console app and then boot up the servers over the network and do anything need to do on that. But that's kind of the projects I've done so far. Gonna stop now. Are there any questions?
I think I asked all my questions already.
Okay. Yeah, it's all right. It's a bit long, and I needed much more preparation than I had. I worked that out about yesterday.
Well, that was cool. Thanks. I read a lot about it, just like on Hacker News or Reddit or whatever, and it comes up. I read about it because it's interesting, but I never really looked much into the details. So this is cool.
What there's a lot to it, and I don't know. I sort of my track was basically I did mostly Rails stuff. Then I got into a bit of Haskell stuff for work, and then did a bit of Go, and then just recently I sort of got into Rust, and like I liked a lot of the stuff in Haskell, but to be honest, I kept on feeling like it was a university project where most of the people using it were doing it for research, not for production applications. And
but I don't think that's just a feeling. I think that's actually what it is, isn't it?
Well, yeah, I mean, there are definitely people, and it's interesting actually because a lot of the people who are involved in Haskell are also involved in Rust stuff. There's a guy who, actually, it's a group of people who wrote a C to Haskell converter that actually converts it so that it's like it'll run identically, and they're all sort of heavily involved in Haskell as well. But yeah, so one thing I didn't actually talk about at all, and I haven't really used it all actually, is there's also a thing called unsafe Rust, which allows you basically to avoid bypass some of the safety guarantees. And what this is useful for is, if you're calling C libraries, a lot of the things, basically C code doesn't enforce any of the things that Rust does. So, it relies on you not making mistakes in your code. But if you're calling stuff, there's lots of situations where you're calling C code where the compiler can't make guarantees about the safety or the memory safety of the way you're calling it. And so there is functions that allow you to basically bypass the security checks in Rust. To be honest, just writing normal applications in it, I haven't touched it. I know libraries that I've used have actually, use it or require it because they're interacting with C code. But for just writing normal applications, there hasn't been the need to actually bypass the type checker, that sort of thing. So
yeah, that was one of the things I liked about it is, worst case scenario, you can still do whatever you did in C. It's not like it's restricted.
Yeah.
Not
well, that was kind of the thing which I was looking at this C to Rust converter, because that's like, wouldn't it be great like porting all the C code, so that we all had all the memory safety constraints. The only problem is, of course, his code, like the converter does literally convert it so it's identical code, so it will run exactly the same, which means if there are safety issues in the original C code, they will be in the generated Rust code because it's identical. But then conversely, if you're looking at, sort of trying to upgrade or port some C code across, then starting with something and then, converting it into more idiomatic code or, it seems to be a reasonable way to go. They've actually got, there's a bunch of libraries that, for SSL and cryptography and things, which some of them started out as ports of bits of open SSL and things. And, then they went through and basically cleaned up all the unsafe code and, now they have sort of libraries that, well, shouldn't have memory safety issues anyway.
Yeah, it'd be nice if like a lot of people could get behind that, because if it's just kind of one or two guys doing it, there could be other issues that create security problems if it could get some momentum.
Well, with the SSL, like I sort of looking at them, they do actually have cryptographers actually checking them as well. There seems to be a fairly big like an ecosystem around Rust, and it also, the people who are getting into Rust and using it seem to be people who are also getting into Haskell and getting into like a lot of the sort of recent research in language design and safety and that sort of thing. So, yeah, it's to me, looking at things like looking for work, it's sort of frustrating because I look at all these places where it'd be a perfect fit and no one's using it because either they don't know about it or they're using Go and they've heard it's difficult.
Yeah, it probably is more difficult than using a garbage collector. I mean, I think there's some truth to that.
Yeah, no, it is. I mean, it is more difficult because it's a bigger scope of what it does. I mean, Go is very limited scope, and if you've got a limited scope, then it's easier. Yeah.
I might say that makes it harder. I mean, if your application has a limited scope and your language has a limited scope and they're the same limited scope, it might be easier. But if your application is complicated and your language is primitive, I think that just makes it harder.
Well, yeah. But I mean, I think they're aiming. Well, from what I saw looking at the Go stuff, it didn't look like they were aiming to replace C. It looked more like, or maybe C in certain domains.
Right.
But yeah, not as a general thing. I mean, I don't know. I wouldn't like to try implementing an operating system in Go.
They definitely aimed low with Go.
Sorry?
They definitely aimed low. They weren't trying to, build a replacement to C. I mean, C is still necessary with Go, unfortunately, for some applications.
Yeah. Well, I mean, I don't know. I mean, I was just surprised because I thought, writing an API for a Google interface wouldn't have been difficult, but it was very, like writing stuff for SOAP in Go was just not fun.
My understanding is Google isn't like embracing Go. Just some people at Google invented it and some teams at Google use it, but I don't think it's like their wave of the future language.
Yeah, well, it seemed to Go seemed to me to be more a good replacement for what people are using Java for, maybe, and also maybe some of the things like Ruby or Python, just because being a compiled language, I mean, it is not like going from something like Ruby or Python to a compiled language is nice in a lot of ways because it tends to be faster, but it's also not having to deal with dependencies at deployment time.
Yeah, you can probably get a lot of performance and a lot of gains by making that kind of issue. I can believe that.
Yeah. Well, I mean, the other one too with some of the Go stuff, it is possible basically to write applications where there are no external, or like there are the absolute minimum external dependencies, which generally is not a good idea. But if you're looking at things like trying to write for lambdas, and you don't want to have to worry about what SSL version is running there, or what versions of the Postgres libraries are there, or those sort of things. It's nice just being able to say, well, I've actually compiled in the version that I tested on and that I've run everything on, and it's all there. And the dependencies are pretty much not much more than a Linux operating system or a...
Right. Yeah, this definitely probably works well for certain things, but I think they just aimed low. They could have done better. All the effort they spent inventing that, they probably could have invented something better with the same amount of investment, but it didn't work out that way.
Well, I mean, my sort of thought, I mean, sort of looking at the history stuff, I think the way Rust was developed actually was a really good model. They did a lot of fiddling around with it and not trying to finalize it, but really working out all the details early on. And so, it would have been hell if you actually tried to use it for anything. I mean, it's one of the ones I was sort of surprised, when they were early on, they were looking at making that Gecko replacement. And you're talking about a language where you haven't really decided what the language is going to be or what the semantics of the language are going to be, and you're writing trying to rewrite a serious piece of application code. I mean, I think it was a good thing because the risk with the language is always that you write code for something that doesn't exist, or you write code that's so disconnected from its application that it's not useful, or it runs into problems that, were obvious if you'd actually used it for anything. But must have been hell trying to, maintain a complex piece of code with a language that was rapidly changing.
Yeah, I think some people just love it, though. They love having all the latest stuff. They don't mind, but that would be rough.
Yeah, but it's interesting because I think it worked quite well for them in that they worked out a lot of the semantic stuff early on, and then they did a lot of cleanup in that sort of type phase where they realized, well, actually half the stuff they had built into the language didn't actually need to be in the language, and could actually just be libraries.
Right.
And that, I think, that worked really well. But it had a long sort of gestation period, and I think that worked. And they also didn't commit to having it baked too early on, because it seemed like, with Go, it seemed like it wasn't ambitious really enough to me. They met all their goals and that sort of thing, and it worked exactly for what they said it was going to do. But then it really wasn't much better than other things. And now they've got the thing that, things like, look at generics. If they're going to bring in generics, that's going to be a really big thing for the language. Whereas before Rust really got baked, they'd already worked out how those things were going to be. They'd tried them, they'd fiddled around with different libraries, made sure that it sort of basically worked. And so at the point where they said, well, we're not going to change this, we're not going to make any radical changes anymore, they'd kind of got it working reasonably well. And so that there wasn't the need. Just looking at, I guess, the history things, you look at the last year and it's like, well, 2 significant changes. There were lots of other, if you look at the change logs, there were heaps of other changes, but a lot of the things that changed were, we actually found out this case was safe and we didn't think it was safe. So we're not going to, like the compiler would throw an error here, but, because we've looked at this more, we can actually show that it's always going to be safe in this case, so that therefore we're going to let you compile it anyway.
Yeah, I think that kind of stuff is fine if you're remaining compatible with the existing code and just adding.
Well, that's the thing with it. It's okay, stuff that wasn't going to compile before, but probably should have, now will compile.
Right.
Or it can work out things that it couldn't work out. One of the ones that's really nice is not having to write the types of everything everywhere.
Mm-hmm.
A lot of that, especially when you're developing. One of the things I've found is, I'm looking at things like compared to Haskell, one of the big pains is it's like, it doesn't kind of fit so well with the development thing where you write a sort of hacky bit that just doesn't enough of what you need, and then you kind of hack on it and play around with it and stuff. It's painful doing that. It's sort of like, you need to write the perfectly complete, fully baked solution from the start.
Good point. Yeah.
Whereas with Rust, it's really nice because basically, you have all these error things, but to start with, what I do is I just write it, and if there's an error, I just say, well, crash, because I don't while I'm developing it, I'm only cared about this one track, that the right track through it.
Mm-hmm.
And so, I work out what I'm going to do, because I might throw away, 90% of that code anyway. So there's no point in, making, completely, working out all my error conditions for code that, isn't likely to, has a good chance it'll never be in the actual application.
There's some syntax, like if you don't really want to handle every error, you can just use some special syntax and it'll just crash when error occurs, right?
No, there's this, basically, like in a lot of these cases, you have an option or your result return.
Mm-hmm.
And there's a thing called unwrap, and all unwrap does is it tries to pull a value out, and if it can't pull a value out, it crashes.
That's what it was, yeah. So if you don't care, you could just use that everywhere until you actually want to.
Yeah, and that's basically what I do when I'm starting, because you want to play around with, you want to work out what it should be first. You don't want to sit there going, okay, well there's 20 possible error conditions in this way of writing it, and do I want to, how am I going to handle all those? You just want to work out, okay, this is the right way through it, and I want to just assume everything's going to work, and then work out whether that's actually how the code should be. And then when I've worked out that's how the code should be, then go back and say, well, okay, well, we actually need to handle all these conditions and say it should throw these errors. I mean, I found in a lot of cases it was things like there are 5 or 6 different ways the error could be produced, but I don't care about any of them. Any of them are the same. It didn't work, and I only care whether this whole thing worked.
Right.
And in those cases, there's a really nice syntax. Actually, sorry, that's something I didn't go through in the option bit. There's a syntax where instead of doing unwrap, writing .unwrap, you just write a question mark, and that does the same as unwrap or returns an error. And so what that can mean is you can do a whole bunch of functions called one after the other and chained, and just put a question mark between them. And what it does is it calls the first function, which returns a result, or so it can either return an error or a thing. The question mark says if it's an error, return that error. If it's not an error, return the result, and then you can call the next function. So you can just chain a whole bunch of stuff with these question marks in it. And
that's kind of new, isn't it?
Well, not that new. It's been around
last year or something. I don't.
It's not the last year. No, that was actually, it was, I think, before. I mean, it was in the history stuff I was reading, so I'll see if I can find the slide, but because it had the date. But yeah, it was fairly early on. Let's see. Okay, yeah, 2006, so November.
2006 or 16?
2016. Sorry. Yeah.
That's not super new. All right. Well.
Yeah, but I mean, it makes writing code where you actually handle all the errors so much nicer, because you can just go. I mean, actually, the other one I found, you can actually, if you've got a bunch of stuff where it's just doing this and checking whether it failed or not, and then this and checking whether it failed or not, and this and if you don't care about any of them, if it's like if any of them fail, you just want to throw a generic error. You can actually wrap that in a not a function, a closure, and then the closure can take a result as its thing, and so you can just put the question marks through, and then just at the end of it say, okay, don't care what the error was, just put this is the error.
Interesting. Yeah, I have tons of boilerplate C code doing that. It'd be nice if there was.
Yeah. Well, it turned what was a huge mess of handling every single different error to I wrote the one error which comes out of it, and then just a question mark for all the other ones that in this long chain of operations. And it just being able to write what is C code or like C code really compactly and really clearly, before you might write a meta language in macros or something like that, so that you could kind of pull out what is a whole lot of repetition to make it sort of more manageable. But there's lots of ways that you can do that really cleanly in Rust. It's sort of it's nice having kind of the advantages of your dynamic languages in a compiled type check language that
there was no reason for those kind of features to only ever be in dynamic languages. It's nice that somebody actually pulled it out here.
Yeah, but I mean, it was sort of interesting because I think a lot of that came around because of the people who got involved in the Rust project